Okay, we want to wrap up the development of the math for 4-bar synthesis and then get into the tactics of 4-bar synthesis. We've looked at this picture now fairly carefully, and we've said that, first of all, this is going to apply to synthesis in that we're going to attach something to this coupler link. And as the coupler link moves, so does the something we rigidly attach to it. And this point P1, as we saw from the airfoil example, P2, P2, P1, P2, P3, three key points in the motion, say, of the airfoil. And we already talked in the last class about envisioning actually attaching the airfoil to this point on the coupler so that the airfoil moves with the coupler. So we need to find the 4-bar points, a moving point on the 4-bar and a grounded point on the 4-bar for this one side that would move the airfoil properly. Once we've done that, then everything we've said about what I'm going to call the left side of the 4-bar is also going to be true about the right side of the 4-bar if instead I name this link W and I name that link Z. Then I would have a vector loop, and it's not really drawn. I would go through W, I'd go through Z, I would go through a P1, then I would come back through a rotated Z that's parallel to this Z. I'd come back through a Z over here, and then I would come back through a rotated W. That was the same length as this link. So I would come back through that one. I would have exactly the same vector loop, exactly the same equations. So whatever equations I develop for this side of the mechanism can instantly be used with no changes to apply to this side of the mechanism. And I just have to have two different solutions from those equations, whatever they are, to come up with a left side and a right side that can move the machine properly. What I can't have is a 4-bar that has two sets of links that are identical. Just this side by itself, even if I doubled up on the links, doesn't make it a 4-bar. All right, so we've already seen our equation. We've already written it down in class. W plus Z plus this delta, which is composed as the difference between the p's, so plus the delta, minus Z times the rotation vector, alpha, minus this W times the rotation vector, beta, equals 0. That's our key dyad synthesis equation. And if we drop down far enough into the document, and we're not going to spend too much time in this document, we will eventually get there. The only difference we see with this dyad equation 815 is instead of passing through delta, they pass through these two R vectors. What are they talking about with those R vectors? Let's go back to the equation. They've said there is a point here somewhere called the origin, 0, 0. Okay? And P1 and P2 and P3, if it exists out here, must be defined in terms of the origin. And so for their vector loop, they went through W and Z, then they backed up through R1, and then they went forward through RJ. Do you see that we can just, instead of passing through the two R's, which locate the two P's according to ground, that we can just go straight through this thing called delta, which is the difference between the two P's. And that's the preferred way to write the equation, in my opinion. And that's the way we are going to be writing the equation. And so let's jump over to Mathcad, and the easiest way for me to write anything while I'm talking to you. And so keeping the picture handy, I'm going to say that our vector loop is W plus, W plus Z. Couldn't go with capitals. I'm going to hit caps lock for most of this. W plus Z plus D control G. What does that give me? It gives me the wrong one. D control G minus minus Z times E raised to the 1I times alpha control G 2 space minus W times E raised to the 1I times beta control G 2, and all of that closes back so that I'm just going to hit control equals 0. And then With that, we can do a little bit of algebraic rearranging. What I'm going to do is move the delta to the other side because it involves entirely known stuff. I'm going to keep the mostly unknown stuff on the left-hand side, but when delta goes over as negative, I'm going to change its sign and change the sign of everything on the left-hand side. So this term will move to the other side, then I'll change the sign of everything. So this becomes positive, this becomes positive, these two become negative. And so this is going to become my W times E raised to the 1i times beta, Control G, 2, minus W, I'm going to bring those terms together, plus, Control Z, I didn't intend that, then plus Z times E raised to the 1i times alpha 2 minus Z. Need to pause for a second. Okay, I had to pause for a second, but I'm back, so finishing this up, let's get back into here and type a capital Z. All of that, control equals delta. I'm not typing very well right now. Hopefully I'll get better, but I don't have too much typing to do anyway. G, control G, no. D, control G. Okay, so just algebraic rearranging. Now, obviously, I can combine these two W terms. Okay, and here's what it will look like. W times parenthesis E raised to the 1i times beta, control G, 2 minus 1, and then plus Z parenthesis, Z times E raised, not typing well at all, raised to the 1i times alpha, control G, 2 space minus 1, close parenthesis, control equals 0. And here is our key dyad equation. And let's look at, well, see, not 0, delta, D, control G. Here's our key dyad synthesis loop equation expressed in a form that's going to be very easy to solve. Okay, because over on the right hand side, remember this delta is simply the difference between P in a particular position, and the equation I wrote was equation 2, P2 minus P1, and I know P1 and I know P2 to start the problem. Everything on the right hand side is known. Looking at the picture, I don't know W and Z until I have the 4-bar. I have no clue what W and Z are at this point. But this term alpha right here definitely has meaning, because that's also part of the standard 4-bar synthesis beginning, in that I've got to specify the motion of the object to be moved. I've got to specify P1, P2, and P3, all fixed to the object. Then alpha tells me how much the object rotates to go from position 1 to position 2. And an alpha 3 would tell me how much the object rotates to go from position 1 to position 3. So those are, so the P1, P2, and P3, alpha 2, alpha 3 are the 5 key known quantities that I have to even start a 4-bar synthesis problem with 3 positions. And so everything known on the right hand side, that involves the P's. Alpha 2 is totally known. Z is totally unknown. Beta 2 is unknown. And W is unknown. And so we're going to have to look at how to solve this thing. And let's see, I need to do one other thing. I'm going to put a subscript here that says delta 2, because this is the delta that goes from P1 to P2. Now I'm going to copy this equation and paste it. And I'm going to change all the 2's to 3's. 3 and 3 and 3. What does this equation say? First of all, the position 3, let's imagine I have a P3 over here. Then delta 3 is going to go from P1 to P3. alpha 3 will be the change in angle from position 1 of z to position 3 of the z vector. Beta 3 will be the change in angle from position 1 of the 4-bar passing through position 2 and going all the way to position 3. That's what beta 3 will mean. And so, again, I'll know the delta 3 because I know P1, P2, and P3. I'll know alpha 3. I have to know that to start the problem. I don't have a clue what z is, I don't have a clue what w is, and I don't have a clue what beta 3 is. Looking at these, let me hit a Control R to clean that up a little bit. What I have at this point is two equations with one complex unknown, w, a complex unknown, z, and an unknown beta 2, and in this equation, an unknown beta 3. So I have, in fact, two complex equations with two complex unknowns plus two scalar unknowns, beta 2 and beta 3. I cannot solve this problem for a unique solution as posed right now, but I'm kind of glad, because if this thing had a unique solution, that means there's only one 4-bar that works, and if I don't like that 4-bar, I'm sort of stuck. I'm not going to have any choices. So I'm really glad that there's not a unique solution, and here's how I'm going to approach the problem. I've got some free choices in this thing. To make this equation set solvable, one thing I could do is I could pretend I know beta 2, and I can pretend that I know beta 3, and if I know both of those numbers, or if I just make up numbers, then all of a sudden this becomes two complex equations and two complex unknowns, the complex unknowns being z and w. So what I can call the beta 2s and beta 3s is free choices. And I've got an infinite number of choices for beta 2, and I've got an infinite number of choices for beta 3. Putting those two infinities of choices together, and it's actually an infinity squared. Infinite choices of this one multiplied by infinite choices of that one will yield one solution. So I've got infinity squared solutions coming out of this pair of equations. With that many possible solutions coming out of here, the chances of finding a few good ones are extremely high. The only problem is that the search could be tedious depending on how I approach the search. But these are the equations that we'll be solving. Now, let's look at these equations in detail because there's something really special about them. Okay, what's special about them is these equations are linear in the unknowns. Yes, I've got exponentials, but if I pick beta 2, and if I pick beta 3, and if I know the alphas, this e to the I beta 2 minus 1 is just a complex constant. It's known. That one's known. These two are known. The only unknowns are w's and z's, and they're not being multiplied by sines or cosines of unknowns. They're not being squared. They are in linear form, and so I can pose these equations in linear form just like equations you've seen before that I'll write out. If I had an equation 3x plus 2y control equal 5 and 5x minus 4y control equal minus 2. This is two linear equations, two linear unknowns. The unknowns are in x of y. And does it change anything if this becomes 3 times e raised to the 2 times 4? No, 3e to the 8 is just another constant. It does not affect the fact that it doesn't change these equations into nonlinear, just because I chose to express a constant using an exponential. And if this 2 became 2 times the sine of 45 degrees. Excuse me. The fact that I'm expressing this constant, and it's still just a constant, in a funny looking way, doesn't make this 2 equation 2 unknown set nonlinear, because the x's and y's are in linear form. The exact same thing is true here. Now, where are the constants in this equation? That's a constant. That's a constant. That's a constant. Same thing in each of the same positions here. So any technique I might have used to solve, and let me just undo some of this stuff so that it looks the way it did earlier. Any technique that might be usable to solve these two equations could also be used to solve these two equations. Now, let me remind you of a matrix way of expressing these two equations, because I can say these equations, in fact, would be a matrix. Let me find my matrix tool, and I'm going to create a 2 by 2 and say OK, and that's going to have a 3 and a 2 and a 5 and a 4, a minus 4, multiplying a matrix with 2 rows, 1 row, 2 columns, wrong, Control Z, let's see, multiplying a matrix with 2 rows, 1 column. Okay. Control equals a matrix exactly like that. Okay. And I'm going to put X and Y right there. And I'm going to put the 5 and the minus 2 right there. And so you recall from somewhere like the 2nd grade, I can take these two equations expressed in linear form and write them as a matrix of constants, the 3, the 2, the 5, the minus 4. Multiplying the unknowns x and y is equal to the right-hand side, 5 and minus 2. This is expressing these equations in linear form. If you have any questions about this, ask me about it in class. I'll say maybe a little bit more about it, but I don't know how to say very much more about it. And there are a multitude of ways of solving equations like this, including a method called Cramer's rule, which is discussed in this document. I'm not even going to look at it. But another perfectly good way to solve this set of equations is to take the idea that a matrix inverse multiplying both sides, and the idea of a matrix inverse which multiplies a matrix produces an identity matrix. So I'm going to copy these equations and paste them right here, and then I'm going to pre-multiply this equation by its inverse, but I've got to make it the inverse. There's my insert key, there's the insert key, and I'll make that an inverse. But then I've got to pre-multiply the other right-hand side by the same thing. Insert times paste. Of course, when I multiply this matrix times its inverse, what I get is the identity matrix, which is the matrix equivalent of 1. Let's just do that. I get the matrix equivalent of 1. And if I were to evaluate this thing symbolically, and let's see, let's bring up the symbolic evaluation. What am I looking for? I'm looking for the symbolic palette over here, which is a little bit off the screen, so I'll bring it up. Move this out of the way. Bring up the symbolic palette. And this whole thing on the left-hand side is simply equal to xy. And of course the thing on the right-hand side is going to be equal to the answer. Copy and paste and hit the equal sign. And it appears that x is equal to 0.727 and y is equal to 1.409. And then if I go back to my original equations, copy and paste. And if I say that x is 0.727 and y is 1.409, although recognize I'm typing approximations because I'm not typing maybe enough decimals. But if I just print this with these values of x and y, that comes out awfully close to 5. And with these values of x and y, this should come out awfully close to 2. And that's just round off error. So the idea of using pre-multiplying both sides by a matrix inverse and solving a set of equations expressed in matrix form as solution equals matrix inverse times the right-hand side is a viable solution technique. So what that means is I'm going to be able to repackage these equations into this form. A 2 by 2 matrix. Okay. And I'm going to create another one. Okay. And then I'm going to create a 4x4 or a 2x2. Okay. Oops, that was wrong. Click right here, create a 2x2. And let's put all this together into the right stuff. I'm going to have W. Clicking in here. W and Z. Control equals this matrix. Paste it right there. Insert inverse. Wrong thing. Inverse. And then times this one. Copy and paste. Didn't quite get it, but I'll fill that in just a second. Copy that one and paste. Don't know why that's not happening, maybe because it's off the screen. Copy, paste. Now, this term, copy and paste, goes there. This coefficient, copy and paste, goes there. This one goes here. Paste, and this one goes here. Don't want the Z. There we go. Copy and paste. And then finally multiplying delta 2 and multiplying delta 3. Get rid of this stuff. Here's the repackaged equation, turning these two linear equations in W and Z, expressing them in linear form, and then getting them ready to be solved. And Mathcad will be able to take the inverse of a matrix of complex numbers, multiply by a vector of complex numbers, and give me the answer. This is how we're going to solve these two equations, two unknowns for complex numbers. Again, notice that what we have on the right hand side, the deltas we know from the beginning of the problem. The alphas we know from the beginning of the problem. Beta 2 and beta 3 control the motion of the grounded input link of the 4-bar. We don't know them, but we're just going to be able to make guesses or make choices, and for every pair of guesses that we make, we're going to get one solution. If we don't like that solution, we'll make changes to these numbers, and we'll guess again, and eventually maybe we'll find solutions that we like. The problem is there are two infinity squared number of solutions, and how do we sort through all of that mess? That's what we'll be using Mathcad for, and we're going to find out there's some very nice behaviors that go on. And here's the basic idea of where we're heading. If I just guess one of these, then there's still an infinite number of solutions left. But if I then guess one, and then I solve the infinite number of solutions based on this one? But of course I can't solve an infinite number of solutions. But what if I sample infinity, and maybe I solve about 360 different values of this one, calculate the W's and the Z's, and those are geometric points, and I plot those points and I see where they lie. That means I can look at a sampling of an infinite number of solutions, and I can see them graphically, and maybe I can come up with some method of understanding where any of these solutions are any good or not. And so that's where we're going to turn next in Mathcad. But the key is this figure, which lets us write the vector loop, W plus Z plus delta minus a rotated Z minus a rotated W is equal to 0. We can do that from a position 1 to 2. We can do that from a position 1 to 3. That gives us two different equations that look just like this. These equations can be expressed in linear form, and they can be solved in a linear solver, and Mathcad knows how to do all of this math. Then we just have to sort through the massive number of solutions and see if they make sense. So with that, we will pause this part of the discussion, and then we'll head to Mathcad and continue.